Well, phew, after that last one, it's time for something a little lighter, right? In this video, I want to talk about using matrices to basically store all the information that we need about a linear system. And so this is really pretty easy, and I think I'll just show you by way of example. So let's say we have this linear system. So I'll just do one in, let's see, I'll do one in 4 variables maybe. Okay, so here's a linear system. This is a system of, we have 3 hyperplanes in 4-dimensional space, and I'm certainly not going to try to draw this or even solve it. I just want to show you how we can store the data in an efficient way. So the only things that we really need to know about these equations is the coefficients, right? Because we know all of them involve these 4 variables, x1 to x4, and a constant term. And we don't, we're writing these things, some of these symbols, over and over and over again. And why should we bother, right? So the way that we can store this information is by kind of breaking it into 2 parts. So we have one part that stores all the information about the left-hand side of the equation, called the coefficient matrix. And it literally just contains the coefficients of all of the terms in this equation. So we have, in these equations. So we have 1, 2, 3 equations, and each one of them involves these 4 variables. And so what we're going to store in each one of the columns of this matrix are the coefficients in the respective equations for the x1 variable. So in the first equation, the coefficient for x1 is 3. In the second one, it's 2, and in the last one, it's 1. In the second column here, we're going to store the coefficient information about x2 in all these equations. So the first equation has coefficient 1, the second one has coefficient minus x3, and the third one has coefficient minus 1. And these are for the x2 terms. For the third column, it's going to be the information about the third variable. So this is minus 1. And be careful looking at equation 2. There is no x3 variable showing up here. So you can put in a 0 for that, because 0 times x3 is going to disappear x3. Right? And then x3 does appear in equation 3, though, so it's got coefficient 1. And then finally, x4 shows up in all of them, so we'll have 2, 1, and minus 1. And that's the coefficient matrix for this system of linear equations. We're literally just pulling out the coefficients for each variable that shows up in these equations. Then there's a vector, a column vector, or sometimes people call this a column matrix, that contains the information on the right-hand side of the equal signs. So we just put in 7, 19, and 7 again, right? These are the right-hand sides of these equations. So together with the coefficient matrix, provided that we're keeping the equation 1 stuff in the top rows, equation 2 stuff in the middle rows, and equation 3 stuff in the bottom rows, we've got all the information we need to, for example, feed into a computer about this linear system. Another common thing to do is to glue these things together in what we call an augmented matrix. So an augmented matrix for this system, the way we would write it is by putting the information in this matrix of coefficients and then a vertical bar to separate out the matrix, this column matrix of constants from the right-hand side of the equation. So this is our coefficients, and these are our right-hand side constants. And that is it. That's how to make an augmented matrix. So let's just do one more easy example. Okay, so if I'm going to make the augmented matrix for this, I would write minus 1 and pi for the coefficients from the first equation. I'll put my vertical bar, and my right-hand side number is the square root of 3. And then down here, I have the coefficient for x1. So again, watch out for the order of these things. Right? So this is, the coefficient of x1 is minus 1, coefficient of x2 is 1, and the right-hand side is 0. Piece of cake, right? Okay, next thing we're going to talk about is elementary row operations.